feeling kind of low, but it has to be done. Has to be done because yeah, it has to be done. Just give me a second. Some of these managers. Hello. Yeah, it is what it is. It's not working. I thought of using my microphone. Man, I'm using everything that I have to make up for it, but I try my best. So I want to watch some conceptual videos on mathematics, some of the underlying mathematics, math for DSA. So I can work some Euclidean. So what's that guy Rene Descartes kind of like made he was talking about I think therefore I am, and he made a lot of forgot what he made. I think he kind of did some mathematical calculus stuff, if I'm not wrong. What did Rene Descartes do? It doesn't matter, but what if there's a lot of math concepts that like overlap, but what are the main math DSA concepts? I think Fibonacci series is definitely one of those things, and we saw DP problem the other day. So what are the let's see. Number theory, GCD, NCD, prime factor. Number theory is fine. Discrete math, not a graph theory. Bipartite graph, it's I forgot what bipartite graph means. Bipartite graph, I think it's something to do with multi-directional thing. Yeah, like one to many, many to one type stuff. Trees, discrete math. I mean, I don't really like see the let's see. I think a lot of yeah. Counting engine. Okay, discrete math. Counting engineering, DP and RL. Okay, DP meaning dynamic programming basically just means you're getting a graph and we're like counting how many times the graph has been used using memoization. That's the main thing. And DSA matrix in graph adjacency. Yeah, if you get some matrix problem in DSA, that kind of like transfers well over. Give me some basic to advanced medium. Matrices problem. Even with AI, I feel like the if we have like a tree like function where you can go on like different tree branches instead of like this linear, sometimes when I'm using, okay bro, like actual, for some reason, Perplexity, I fuck with my boy Aravind, he is a goat. I don't know, let's see, lead code, matrix problem, the tree 2D matrix, that's exactly what I want. Traversal and manipulation rather than 48. Let's go. Hopefully it doesn't lag. YouTube can go back. Don't really need it. Rotate image. Do not allocate 2D matrix and do. I want a matrix problem. Matrix sounds fun. Sounds fun. You have 30. I think I've already did one, which is the medium 2D search matrix. Basically, it's nothing to do with matrix. It's I mean it kind of is in a way, but let's do easy. So island perimeter, I should also get the tags. Depths for search breadth. Okay, island perimeter is a DFS problem. Hopefully, like, let's look at some of the hard problems, because why not? Cancel this. Hard problems. Sudoku, word searcher, best meeting. So there's a lot of overlapping with linear algebra. Is there an overlap? I don't think so. Probably, right? Should be. Mainly through operations like 2D matrix and multiplication, but in machine learning, everything is 3D, right? Okay, 1D. Audio and signal tokens are like in 1D. Grayscale image and RGB image are in 3D. So, okay, that makes sense. Batches, like, okay, batches make sense. A lot of NLP language models. Okay, language models are 4D, isn't it? NLP embeddings, cool. So what are we doing? Let's, should I do a problem? Like a best matrix progression. Pretty sure there should be one. Fuck, that was hot. Reshape the matrix, basic. Five. No. No. 566. Oh, there's no hard. Simulation. What the fuck does that mean? Let's reset. So in MATLAB there is a handy function called reshape, which can reshape an n by matrix. Bro. Okay, you're given an MNX mat and two integers R and C representing the numbers of rows and numbers of columns of wanted reshaped matrix. In reshaped matrix should be filled with all elements of the original matrix in the same row, transversing. Okay, if the reshape operation with given parameters is possible and legal output. Okay.
So
Rotate image 48. Okay, you're given a. Why is this medium? Oh my god. Is this a hard question?
hey everyone, welcome back. Let's write some more neat code today. We're given an n by n matrix, so this time it's a square matrix for sure, representing some image, and we want to rotate that image by 90 degrees clockwise. And we are required to do this in place, so we cannot allocate more memory. We can't just make a copy of the matrix and rotate it like that. So the challenge here is definitely doing it in place. You can see that they had a original matrix like this. What they did is they took the 1
using CAD on it, and I don't know. So I know here.
Okay.
So before we start, so I just wanted to give you the crux of solving, let's say in an interview you are given any matrix problem, right? So the thing is, whenever any matrix problem is given to you, so how you are going to approach, how you are going to think in that direction, right? Because the thing is, you'll hardly have around 5 to 8 minutes of time to think. The interviewer will give you around that much time, correct? So the thing is, you need to think in that way. So if you will be pre-calculating stuff beforehand, right? If you know that in which direction you need to think, then in the interview it will be easier for you guys to come up with a solution, right? So for that purpose, like basically whenever any matrix problem is given to you, right? So any matrix problem can be divided into 3 parts. Is this all?
Okay, logic based auxiliary array using two pointers,
Point
BFS,
presentation
DFS.
visible to you guys?
Yeah.
Awesome. So any matrix problem, it can be divided into 3 parts. Either it can be solved with the help of a logic based on the question that is there, and the second part is on the basis of the breadth first search, and the third is on the basis of depth first search. So normally this breadth first search as well as the depth first search, it's normally applicable on trees as well as graphs. So I'm going to definitely cover them in trees as well as the graphs when we'll be covering that data structure. But it is very much important for the matrix questions as well, because let's say if I don't cover over here in matrix part, right, this breadth first search and the depth first search, and let's say if I try to teach you over there itself and then give you 1 to 2 matrix problem, then right, then you guys won't be able to like correlate with this matrix questions, right? Because since the matrix question I can only cover this logic based questions, right, that is for the matrix part, and if I leave this breadth first search and depth first search for the later part, then I think you guys will be having a little bit of trouble in basically thinking collectively. So that's why I am teaching this breadth first search as well as depth first search in this matrix part as well, and as well as when we'll be covering trees as well as graphs, I'll teach over there as well, because the way that we're coding, right, it is a little bit different for the matrix as well as for the trees or the graphs. So that's why it is very important, and the thing is this breadth first search and depth first search is very important, and you guys are definitely going to encounter questions on the basis of breadth first search and depth first search on the matrix part. So today's lesson is very important because there are a few more logic based questions that are there in the matrix which needs to be solved, and once that is done, right, I'll move to the breadth first search by the end of the class today, and then if time permits, then I'll try to cover the depth first search. Otherwise, in the next weekend.
Nigga, why you yapping? Stop yap maxing. Nigga, stop yap maxing. Nigga, this nigga just yap maxing. Bro. No. You're all getting it wrong. Give me a matrix question. Give me a matrix graph edges adjacent. Graphs. Okay.
Hey
So
guys,
let's see
Rick
what he
here.
has
I'd
to
like to talk
say.
about a really common data structure known as graphs. Now, if you've gone through this course, you actually have already seen a bunch of graphs. Trees are a stuff.
Yeah, this nigga for some reason has really good videos. Fucking hell.
Suppose you were given a graph with a starting vertex and asked the question of finding the shortest path from that vertex to every other vertex in the graph. The BFS algorithm allows you to answer this question. In this video, we will go over the key information behind this algorithm, which
Now
will
there's
then lead us to
empty
an overview
space
of
over
implementation of
here,
BFS.
and what it gets padded by actually depends
Hey guys,
on
Rick
the
here.
right
Today I'd like
shit.
to talk about a really common data structure known as graphs.
Now, if you've gone through this course, you actually have already seen a bunch of graphs. Trees are a subclass of.
Today I want to go over another key search algorithm in graph theory, breadth first search or BFS. Suppose you were given a graph with a starting vertex.
Isn't it crazy, bro? He can make a video. Okay, bro, isn't that crazy? He could just make a video on this. Let's just like kinda go over all of them. Yeah, there's 5 steps to like do a dynamic problem. Crazy. How the fuck do you get this good? This okay, let's do DFS first.
In this video, we will take a look at our first graph algorithm, depth first search, or more informally DFS. This algorithm is one of the most
Didn't this nigga, what do you do? He did a graph theory one. Bro, this is some Kabbalah shit.
In
The
this
fuck?
video, we will take a look at our first graph algorithm, depth first search, or more informally DFS. This algorithm is one of the most fundamental algorithms in graph theory, and many of the ideas in this video will carry over to more advanced graph algorithms. For that reason, in this video, I'm going to spend some extra time building intuition for the ideas behind this algorithm. Here's what you can expect to get out of this video. We will first introduce the concept of a graph traversal and what that even means. Then we will try to build our own graph traversal method and show how it intuitively leads to the core ideas of depth first search. Once you have an idea behind what depth first search is trying to achieve, we will then spend some time going through the implementation of DFS in a visualized manner. And then we'll finish off this video with some really cool applications of depth first search that I'm sure you're not going to want to miss, so make sure you stick to the end of the video. Let's get started. Given a particular graph, one useful ability involves starting at a single vertex and finding a way to get to every other vertex of the graph. The formal name for this ability is a graph traversal, which is simply defined as an algorithm that
So graph
visits
traversal.
every vertex of the graph. There are several graph traversal algorithms, and they are primarily differentiated by the order in which they visit vertices. In this video, we will focus on the DFS order. So now that we know the basic idea behind the graph traversal, let's take a step back and see if we can sort of invent our own graph traversal. The line of thought that I'm going to present here is actually exactly the DFS algorithm. The goal here is to show you how the DFS algorithm is really a surprisingly intuitive idea, something that with some thought you probably could have come up with on your own. Let's take a crack at it with this graph. Given a start vertex, we want to find an order that we can go through the vertices of the graph so that we guarantee that we end up visiting every vertex. Let's start with vertex 0. From vertex 0, we have a couple of options for how we might want to continue. The option we choose doesn't really matter too much here since our hope is that we'll eventually explore all the vertices anyway. Let's say that we choose to visit vertex 1 from here. What now? Well, now that we're at vertex 1, we have a new set of choices for where to go next. It doesn't really make sense for us to go back to vertex 0 since we've already seen it, so let's pick a new vertex to explore. Let's go with vertex 2. And from vertex 2, we only have a couple of options, namely going to vertex 0 or vertex 1. But we've already seen those vertices, right? So what we might naturally do is say, okay, there's nothing further we can do from this vertex, so let's take a step back to where we came from, which is vertex 1. And from vertex 1, we now have 2 unexplored vertices that we can then go to. Let's go to vertex 3. From vertex 3, our path forward is pretty set in stone. The only unexplored node is vertex 5, so let's go there. From vertex 5, we have a few options on how to continue traversing the graph, and let's go ahead and pick vertex 6. At vertex 6, we've now reached another dead end similar to what happened with vertex 2, so let's retrace our steps back to vertex 5. From vertex 5, let's say we pick vertex 7 as the next node we visit. From vertex 7, the only path forward is to vertex 8, and from there, we again have only one choice leading us to vertex 9. At vertex 9, we've now hit another dead end, so let's go back to vertex 8. Now what's different this time is that from vertex 8, we've already explored everything there is to see, so let's retrace our steps once again. We got to vertex 8 from vertex 7, so let's go back to there. From vertex 7, we have the same story, so we go back to vertex 5. And everything from vertex 5 has been fully explored, so from vertex 5, we now go back to vertex 3, which was the vertex that got us to vertex 5. Same story here, so let's take one more step back to vertex 1. And now that we are back at vertex 1, we have finally found a new undiscovered vertex. So we now visit vertex 4. From vertex 4, there's nothing new to explore, so we go back to vertex 1, which now also has nothing more to explore, which finally leads us back to vertex 0, which now is also completely explored. And now that we're back to where we started,
So this path doesn't matter, it's just the nodes that matter.
we have traversed every vertex of this graph. So I know that was a lot, but the philosophy of how we explore this graph by continuing to explore new vertices as we see them until we hit a dead end is what depth first search is all about. When performing depth first search, think of yourself as a bold and adventurous explorer, where every time you see a new vertex, you will continue to explore new vertices until you hit a dead end, in which case you'll retrace your steps and continue exploration. It's worth noting that there are actually several valid depth first search orderings for this graph. Let's go through one more valid ordering as an example, and also as further familiarization and practice with the core idea behind DFS. We can generate another ordering by just changing up the choices of vertices to explore whenever we have a choice while sticking to the core philosophy. Let's start again at vertex 0, but now when we have a choice between choosing vertex 1 or vertex 2 as the next node to explore, let's pick vertex 2. Last time we went through this, if you remember, we picked vertex 1. Again, I want to emphasize that both of these choices are valid, and if you were ever asked for the DFS order on a test or an exam, the instructions must be clear on how to make these choices.
So
You
this,
must always pick the node with the
this,
smaller value when you have a choice.
this,
In that case, we would have picked vertex 1.
this,
Anyways, back to what we were doing after visit vertex 8. The next vertex helps to try figure out the implementation on a smaller graph since it has fewer moving parts. Here's one valid DFS order.
So capital G is graph, comma 0.
One thing that you may have noticed about this process through the examples that we've done so far is that it's actually naturally recursive. We start at a particular node, and once we visit that node, it's almost like we can ignore that node in the graph and run DFS on all of the neighbors of that node. So this inspires one initial idea for how we might implement DFS. Given a particular graph G and starting vertex V, we first visit V. Then for each neighbor of node V, we can run DFS on the graph with that neighbor as a new starting node. Remember that we are representing graphs using adjacency lists, so an operation of finding the neighbors of a node is quite simple. So let's try the first attempt at an implementation and see what happens. We start at vertex 0, and let's say that the first neighbor we end up picking is node 1. So that's the next node we visit. We then go through the neighbors of node 1 and repeat the process. But there's one big issue with this implementation. Take a second to see if you can figure out what the problem is. The issue here is that when we iterate through node 1's neighbors, one of those neighbors is node 0. This means that with this current implementation, we'll end up calling DFS on node 0 once again, which would create an infinite cycle of recursion. So, how can we fix this? Well, what we want to do is ideally only call the DFS function on nodes that we've never seen before. One way to do this is to essentially mark nodes that have already been visited. We can do this by maintaining a list of Boolean values where each one is mapped to a vertex of the graph. Initially, all these values will be false since we haven't visited any vertex.
It's gonna be a 0.
We can mark the vertex as something we've seen before by changing the respective
Yeah, you could do that, yeah.
index to true. Now with the vertices marked appropriately, we can now call DFS recursively on a vertex.
So G would be the graph, V would be the starting point, and visit V.
If that vertex is not
Okay.
currently marked. Let's dig a little bit deeper to verify that this implementation actually works. We first call the DFS function on our graph with starting vertex 0. This will then visit vertex 0, giving us the first vertex of our traversal. After that, we mark the vertex and begin looping through the neighbors of vertex 0. Let's say the first vertex from our neighbors we looked at is vertex 1. What happens now is that we make a recursive call to our DFS function with a new starting vertex of 1. The first thing that happens in this recursive call is we visit vertex 1, which becomes the second vertex in our DFS traversal. Now the key idea is that when we look at the neighbors of vertex 1, vertex 0 is already marked, so we can't make another call to vertex 0. So the only remaining option is to recursively call our function on vertex 3. The process is exactly the same. We visit vertex 3, which ends up being the third vertex in our DFS traversal. Now from here, we can go to vertex 2, or we can go to vertex 4, and the choice we make here is arbitrary. Let's say the algorithm picks vertex 4 first. This means that we have another recursive call with the starting vertex now assigned to vertex 4. We then visit vertex 4, which is the fourth vertex in our traversal. Now at this point in the recursion, we now look at all of vertex 4's neighbors, which includes only the vertex 3. But notice that vertex 3 is already marked, so what that means is at this point there's nothing further to do in this call. So we go back to the previous call of the DFS function on the starting vertex 3. We had just finished our call to the neighbor vertex 4, so let's now evaluate the next unmarked neighbor. The only remaining unmarked neighbor is vertex 2, so we can make a recursive call to the function with starting vertex 2. In this recursive call, we visit the vertex, and that becomes the fifth vertex in our traversal. There are no more unmarked neighbors for vertex 2, so we can go back to the call on starting vertex 3. Vertex 3 also has no more unmarked neighbors, so we can go back to the call on vertex 1. Same story here, so we go back to our first initial call on vertex 0, which also has no more unmarked neighbors, which means at this point the DFS traversal is complete. Pretty elegant and simple algorithm overall, and I hope drawing out the recursion gives you a better understanding for why this algorithm works. There's one more implementation of DFS that I think is equally important to understand. This is an iterative implementation where we have the same concept of marked nodes as before, but the key difference now is that we will use a stacked data structure to keep track of nodes to visit. So at the start, we will initialize a stack with just starting vertex, and then while the stack is not empty, we'll pop off the last vertex of the stack. If that vertex has not been visited before, we will visit the vertex and mark.
This is a recursive one. Shik. This is a stack one.
it accordingly.
So, okay.
Afterwards, we'll iterate the neighbors of this vertex as we did before and insert them into the stack as long as they haven't been visited before. The best way to understand this implementation of DFS is by seeing it in action. When we call this function on this graph with starting vertex 0, we start off with a stack that contains just vertex 0. We then remove this vertex from the stack, and this is consequently the first vertex that we visit and mark in the graph. As a result, it's the first vertex of our DFS order. Now we iterate through all vertex 0's neighbors, and since none of them have ever been visited before, we add them all to the stack. We then go back into a loop and pop off the last inserted vertex, which happens to be vertex 1. This vertex has never been visited before, so we now visit this vertex and mark it. This is the second vertex in our order. Now, as before, we go through the neighbors of vertex 1. Vertex 0 has already been visited, so we don't insert it into our stack, but since vertex 3 has never been seen before, we'll put it in our stack. Notice that vertex 3 shows up multiple times in the stack, but that's okay. The marking of vertices ensures that they won't be visited multiple times. The next vertex we pop off is vertex 3, which we then visit, mark, and add to the order as the third vertex. Vertex 3 has 4 neighbors, but only neighbors 2 and 4 have not been visited before, so these are the next 2 nodes we add to the stack. After adding these nodes to the stack, the next vertex we pop off is vertex 4, which means it's now the fourth vertex in our DFS order. Vertex 4 has only one neighbor in vertex 3, but since that vertex has already been visited, we do not need to add it to the stack. The stack is still not empty, so the next vertex we take out is vertex 2. This vertex hasn't been visited yet, so we visit, mark, and add the vertex to our order.
Okay, what's
We now
the
visit all vertices
difference?
typical applications. Both these. So you've seen two implementations of DFS thus far, and I want to make an
Bro, I think personally this is better.
important note that for all practical applications, both these implementations are equivalent in the sense that they both run in the same running time of O of v plus e time, where v is the number of vertices in your graph, and e is the number of edges. As a result,
This is
from a
clearly
performance
better.
perspective, if you run either of these algorithms on a huge graph, you'll see no noticeable difference. However, the reason I want to show you both versions is that the recursive implementation is the more standard implementation of DFS you'll encounter, since it's cleaner and easier to read. But at the same time, including the iterative approach is important since it's more generalizable to other graph traversal algorithms that require an iterative approach. You'll end up seeing this logical structure a lot in other graph algorithms, so I think it's a good idea to introduce it here.
Okay, so in BFS, a lot of iterative approach is used, so it is better to just know the iterative way to do a DFS. Fine.
On the topic of comparisons, let's make a quick note about the differences between a pre-order and post-order DFS traversal. The orders
So
we have
pre-order, I almost forgot.
looked at thus far are
Remind me.
pre-order DFS traversals. All this means is that we output a vertex as part of the order as soon as we encounter a new vertex. A post-order traversal is slightly different in that we're going to output the vertex as part of the post-order only after there's nowhere else to explore from that vertex. For example, in this graph, the first vertex in our DFS post-order is 2, since that was the first vertex where we hit a dead end and had to go back. The next vertex where this happens is vertex 6, which then ends up being the second vertex in our post-order traversal. And eventually we reach another dead end at vertex 9, which then becomes the third vertex in our post-order. Now vertex 8 is also a dead end, so we can add that to the post-order. The previous vertex 7 is now also a dead end, and this continues until we get to the starting vertex. Here's what the rest of the post-order traversal looks like. And as with pre-order traversals, there are several other valid post-order traversals for this graph. The important idea here is to make sure you understand that a DFS post-order will only add a vertex to the order when there are no more neighbors to explore at that vertex. Implementing a post-order DFS traversal is actually quite easy once we have a pre-order implementation. This is what the recursive pre-order implementation of DFS looks like that we just went through. To make it a post-order implementation, all we have to do
You just have to. Let me guess. Post-order, you just have to do it after. You need to assign it
looks
after
like that we just went
here.
through. To make it a post-order implementation, all we have to do is instead of visiting a vertex as soon as we encounter a new vertex, we will now visit a vertex only after all its neighbors have been visited. This idea is reflected by just moving the call to the visit
Yeah,
function to the very
visit
end of
her.
the DFS post-order function. And that's all there is to DFS post-orders.
Bro, have I done post-order before? Pretty sure. Fucking never say that word, please. Graphs? No. Trees? Oh, it's binary tree. It's binary tree. What I did is binary tree. But anyways, I think it's the same thing. We did it with recursive, but it's in a binary tree. So it's either one or that. Okay. But it's same thing goes for the. Pretty sure same thing goes for the graph too. So let's look roadmap and let's look graph. Practice graphs perimeter yeah, post order traversal. I'm pretty sure it's the same thing to graph too. So same thing for trees. Binary tree, post order.
last part of this video, I want to talk about some of the applications of DFS. DFS with some additional modifications can solve a ton of interesting problems in graph theory. One example is cycle detection. This problem can be solved by applying DFS with the additional check that anytime you encounter a new edge that points to an already visited vertex, you have a cycle. Another example is finding connected components of a graph, which just requires running DFS multiple times. The main idea behind finding connected components is to start by running DFS on a random vertex. DFS will then find one component. The next step is to then run DFS on an unvisited vertex, which will output another connected component. Continuing this until every vertex is visited will give you all connected components of a graph. Another more involved application of DFS involves finding a topological sort of a graph. This feature applies to specifically directed acyclic graphs. Imagine each vertex in this graph represents a task. If an edge points from vertex 0 to vertex 1, as it does here, what that means is that task 0 must be done before task 1. A topological sort basically answers the question of how we can find a valid order to execute tasks in a directed acyclic graph. This particular graph has several topological sorts, one of which is to start with task 0, which allows us to execute task 1 and task 4. From here, we can move on to task 3 and then task 5. From task 5, it's important to note that we can't actually execute task 8 until we finish task 7. So we execute task 7, which now unlocks task 8 and task 9. After this, we can go back and complete task 6 and task 2. Again, this is just one possible ordering. There are several other valid topological sorts. This problem can actually easily be solved with depth first search, specifically a DFS post-order traversal with a few modifications. A DFS post-order on this graph will give you the following as one possible output.
How do you know if
Do you notice anything
post-order?
interesting? The key idea is that reversing the post-order traversal of a graph will always give you a valid topological sort of the graph, and I encourage you to think about why this trick works. There's a fairly intuitive justification for why this works that I'll leave to you as some food for thought. The last application I want to talk about is kind of just a fun one that I
What the fuck is this
The last
topological
application
sort?
I want to talk about is kind of just a fun one that I learned about while doing some research and inspiration for this video. Turns out that you can easily generate some really cool mazes with DFS. Most mazes have a grid as a foundation, which we can easily represent in a graph. Now, with this graph representation, we can run a modified version of DFS from a particular starting point.
So apparently reversed post-reversal. No. Post.
At the top left corner and check out what happens. What's really cool about this is that the only difference here is that instead of inserting neighbor nodes one at a time in a particular predefined order, we take the set of neighbors of a node and randomly insert them into the stack. When I generated this animation, it was just a couple of lines in difference from the bare bones DFS algorithm. And it really does generate a difficult and beautiful maze. I had a hard time solving it without cheating, so good luck for those of you who want to try.
Shik. Bro, this is so easy.
Generated this animation, it really does generate a difficult and beautiful.
So let's go here. Check. Let's go here. Let's go here. Let's go here. No, let's go here. Check. Let's go to pa. Bro, I think I already found now. This is a dead end. That is a dead end. That is a dead end. Okay. This is a dead end. Dead end. Dead end. Dead end. Dead end. Dead end. Yeah, it's either this or this. So shook. Dead end. Shook. Jig. Oh, so close. So close.
Beautiful maze. I had a hard time solving it without cheating, so good luck for those of you who want to try. That's all for this video, and thanks for watching. If you enjoyed the content, please hit the like button so that this content will be recommended to more people. If you want to see more content like this, please don't forget to hit the subscribe button. And if you want to
Search how map application finds a source short of root. I don't know how PNG works. I don't really care. Breadth first search. So I was doing some DP yesterday, a little bit. Fourier transfer. I don't really care for Fourier. Dynamic array. Word of any recursion problem. Dynamic arrays. What is in a dynamic array? Never. Tower of error, complete recursion visualization. What is a topological sort? So, what the fuck is a topological sort? Give me YouTube shots, nigga.
Now let's solve course schedule. We're given a bunch of pairs of courses. So for example, before we can take course B, we have to take course A first. And maybe before we can take course C, we also have to take course A first. But before we can take course D, we have to take C and we have to take B. Is it possible for us to take every single course? In this example, it is. We first start out with course A, but after A, we can then take either this one or this one, and then after we take both of them, we can then take D. Add a line from D back to A, it is now no longer possible. So this problem is all about cycle detection. It's just building an adjacency list. We're given the edges and we want to convert it into a graph. Then after that, we're going to initialize a queue for our breadth first search. We're only going to add the nodes that don't have any prerequisites. After that, we do a basic breadth first search down here. Now let's solve course schedule. We're given a bunch of pairs of...
Yeah, I can kind of see it. Topological sort. Why is he, bro? It's basically like creating a topological sort lead code. He has topological sort in the thing. Interesting. Hard question. Fuck. You just have to like basically memorize it at that point.
Write some and lovely
Where is topological sort even? I mean, it is just a breadth first search, but anyways, that's topological sort. A lot of big brain ideas. What even is this?
At some point, when you were learning how to program, you probably encountered a written code that looked like the following. You start with an empty array, and then you add elements to it one by one.
Mm-hmm.
Accessing any of the 5 elements in the array is really quick and simple through an index. You also have the ability to remove elements from your array fairly easily. All of these features are cornerstones of a fundamental data structure called a dynamic array. One key feature of dynamic arrays are that all of these insert, access, and remove operations are incredibly efficient. When you're learning the intricacies of a programming language, though, it's easy to just note the features of these dynamic arrays and move on to cooler applications of these data structures. But underneath the hood, there's a lot of clever thought that's put into making these arrays extremely efficient. In this video, we're going to kind of peel away the abstraction and really understand how these dynamic arrays work. And most importantly, I hope that you can come away from this video with a perspective of how you might have gone about inventing this robust data structure. So let's start to think about how we might start. Whenever you start off with a somewhat ambiguous problem, we generally want to simplify it. We're going to start off with this pretty reasonable simplification. Let's first try to build a data structure that focuses on only accessing and inserting elements quickly. So for now, we're going to forget about the remove operation. The first thing we have to acknowledge is that whenever we want to start adding many pieces of data, we're going to have to store it somewhere. The storage hub on your computer has a large amount of memory, all split into nice, organized, and evenly spaced blocks. And whenever you want to start storing some data in a computer, we must allocate a small fixed length portion of this memory. This is a key constraint. We can't just say we're going to use some portion of memory and then try to use more. The computer is not going to be a fan of that. In computer science, we often call this a fixed length array, and many programming languages allow you to create a fixed length array easily. So, what do we have going for us with this fixed length array in terms of getting to our final goal of a dynamic array? Well, we can place data into this array very quickly. We just have to tell the computer to store the respective data in that portion of memory. Once the data is inserted, we can also access elements quickly. The computer knows where the fixed memory segment starts, and each piece of data is stored in an evenly spaced block, so it's quite easy to find an element using an index. Anyways, so it looks like the scheme works perfectly if we just add 4 pieces of data. Adding elements is super fast, and so is accessing them. But when we are creating a dynamic array, we are often not going to know how much data we have ahead of time. we could be dealing with a few hundreds of samples, or we could be dealing with billions. Whenever we create a fixed length array, there's a chance that we run out of space and have to add space. Let's think about our options. What should we do when we get a fifth element? The first thing that comes to mind is we can just create a new fixed length array to accommodate additional data. Once the original fixed length array reaches its capacity, we create a new array of length one more than the previous array. Now, since
And
when
move
we create
everything
a
into
fixed length
that.
array of size
Yeah,
5,
that
and
makes
this one
sense.
empty, we're going to have to copy the elements one by one to the new array. And then, when we add a new element that fills the capacity of this array, we're going to have to repeat the process.
Yeah, it's gonna be time
So you might
complexity,
be looking at
bro.
this scheme and thinking, this feels wasteful and, well, just kind of plain bad. This just can't be the right way to do it. Let's follow this intuition and see if we can develop a way to quantify how bad this really is. Let's start with some simulations and try to determine the amount of work it takes to insert a particular number of elements. What do I mean by amount of work? Well, in a sense, I'm being intentionally vague because there are many interpretations of this. So let's ask ourselves, if we were doing this process by hand, what are things that take effort? Well, it definitely takes some small unit of effort to insert some data into an array. And it also takes some effort to draw and keep track of the boxes that represent an array. So let's actually count these two things. We'll count the number of insertions, and we'll also count the length of the current array that we are using. The first metric will give us a sense of how much time the scheme takes, and the second metric will give us an idea of the amount of space required to execute this scheme. So let's run this and see what happens. If we start with 4 elements and insert elements one by one, this is what it looks like. Remember, we have to create a new fixed length array of size 1 more than the previous array, and copy things over each time we have a new element that does not fit in the previous array. One thing to note here is that I'm only going to count the final array as a new space we're using, since we can easily get rid of previous arrays when we generate the new array. After 18 elements, we end up having 165 insertions, and our final array uses 18 units of space. If we continue doing this, after 1,000 elements, we end up having around 500,000 insertions and 1,000 units of space. Going even further, after processing 1 million elements, we have over 500 billion insertions and 1 million units of space. To give you a sense for how intensive this scheme is, I ran this on my personal computer and it took about 12 hours. These are some nice data points, but what about in general? Some of you may have noticed a pattern here, and we can absolutely use this pattern to define a more general mathematical function of how our insertions in space grow with the function of the number of elements.
It's like a Gaussian thing.
The space function is quite straightforward. If we're inserting n elements using the scheme, we'll be using n units of space.
Yeah.
How do we go about counting the number of insertions? Let's see if we can write it out. Assuming we first initialize 4 blocks of memory, as we've done so far, we first insert 4 elements. Then we resize and copy over 4 elements. Then we add our 5th element. Then we resize again, copying over all the 5 elements.
Yeah, it's a
Add the 6th
Gaussian
element.
thing.
This pattern continues until we insert our last n element. We can rewrite the sum into a little bit of a nicer format to work with. If this resulting summation isn't immediately familiar to you, there's a cool geometric way to divide the sum. When we sum these elements, we can think of it as building a triangle of base n. And our total sum is the number of blocks in this final triangle. How can we go about figuring that out? Well, notice that if we copy over this triangle and rotate it, the number of blocks in our triangle is half the blocks in the rectangle. The number of blocks in the rectangle is equivalent to the area of the rectangle, where each unit is a single block. This means that our rectangle has n times n plus 1 block. Consequently, the result of the sum is n times n plus 1 divided by 2, which is also sometimes called Gauss's formula. Simplifying our final expression, this then means that the number of insertions is 1/2 n squared plus 1/2 n minus 6. This assumes that we of course have at least 4 insertions. Okay, so now that we have a precise way to quantify the scheme, it seems like our resizing scheme is lacking. What can we do to make it better? Specifically, can we see if we can reduce the number of insertions, since that seems to be our biggest bottleneck? Think about this for a moment. Feel free to pause the video to brainstorm. What if instead we increase its capacity? We are only increasing its capacity by 1. What if instead we increase its capacity by something larger, like 8? This allows us to not have to resize the array every single time we insert an element, so on the surface, it looks like it's already better. Let's repeat our analysis to verify this. After processing 18 elements, we now end up having 36 insertions and 20 units of space. This is definitely an improvement. We tried to scale it up to 1,000 elements. This is what compute has to do while processing with resize for 997 elements. After inserting 1,000 elements, we have 63,500 insertions and 1,004 units of space.
Is that where the 8-bit comes from?
2.5 billion insertions and 1 million 4 units of space. In general, the number of units of space we need to insert any n elements is going to be at most n plus 8 units of space. We can also find a more general version of the number of insertions, although the algebra is a little bit more involved. I don't want to get too deep into the matrix used here, since it's not really the point, but a quick summary is that since the sequence that we have here is a sum of evenly spaced numbers, we can calculate the average and multiply it by the number of elements in the sequence, and to make the algebra work out nicely, we assume that after n insertions, the array is completely filled with elements. This assumption doesn't generally affect the trend of this function, it gives us a good estimation. So, let's take a moment to take stock of our analysis thus far. We found the general trend in these two resizing schemes. Clearly, resizing by 8 elements is a smaller function for all reasonable inputs. But how much better is it really? Remember, for 1 million elements, we still have 62.5 billion insertions. And more generally, what happens when n becomes very large? What's going to dominate? When n gets very large, the term that plays the biggest role in this output is the n squared term, which both functions share. This leads into a very important concept when it comes to quantifying the performance of data structures. When you are coming up with these general functions, you need a lot of work with evaluating summation. In reality, computer scientists are notorious for these. We just want the least amount of information that captures the essence of the performance of a data structure. Computer scientists generally don't care about the specifics of the exact function that captures the performance of a data structure or an algorithm. They care more so about the dominating term and use that to encapsulate what we call the runtime of an algorithm. They use specific notations for this called big O notation. In this example, inserting n elements into a dynamic array with this resizing scheme takes O of n squared time and O of n space. And using big O notation, you can see that even though the resize scheme of adding 8 blocks at a time may initially seem better, on a large scale, it doesn't actually perform any better than our first resizing scheme. And we actually can generalize this. There's nothing special about 8 elements. If we perform a resize of k elements, even if k is a very large number, in the grand scheme of things, our dynamic array still performs n insertions in O of n squared time. It's also worth noting that a scheme where k is very large is not very desirable, since a large chunk of the allocated block in our dynamic array will not be used. The question now is, can we do better than this?
In the next video, I'll show you how programming languages such as Python and Java can reduce data structures using a surprisingly simple and clever trick that reduces the runtime for n insertions to O of n time and O of n space.
By recursion? I don't know.
In the last video, we introduced the dynamic array and found that a key issue in implementing this data structure is coming up with an appropriate resizing scheme. We tried a couple of initial resizing schemes and found out that both of them performed n insertions in quadratic time. I ended the last video with a question about whether we could do any better, and in this video, I'll
That's what I was thinking. It doesn't really like change it. You're still like doing it. It's still the same thing, isn't it?
simple yet elegant scheme that modern programming languages use to implement the dynamic array.
Let me guess.
What's the core issue with the scheme that we've looked at so far? We know that the operation is taking
I don't know.
to the resizing. So a really good scheme is going to try to limit the number of resizes. Right now, when we refactor by adding a constant number of elements, at some point when our dynamic array gets really large and we continually add elements, we're going to be doing a lot of resizes where we're copying over a ton of elements. A better scheme would have to find a reasonable way to limit the number of resizes. So one idea that may come to mind is to scale our resize depending on the size of the current fixed array. What if we resize the array by a factor of 2 each time its capacity is reached? Let's see how the analysis of this plays out. When inserting 18 elements, we end up with a total of 46 insertions and 32 units of space. And if we continue this, we have 2020 insertions and 1024 units of space for 1000 elements. Notice that the insertions for the last few elements are just into an already allocated array. We didn't have to do any copying from the previous array to the new one. When we move to 1 million elements, we have about 2 million insertions and about 1 million.
Oh, I just doubled the thing. Okay.
So let's see if we can generalize this as before. In terms of space, our new algorithm is at most going to take 2n blocks of memory to insert 10 elements, which is O of n memory. Moving to insertions, what's a good estimate for how many insertions it will take for this resizing scheme to insert n elements? We once again first insert 4 elements. Then, after doubling the size of the array, we insert 8 elements.
2n.
And this continues until we insert the final n elements. We're going to assume n to the power of 2 to make the math nicer. We can slightly rearrange the sum to make it easier to work out. If it's not clear how to proceed, there's another cool geometric perspective that we can take to evaluate the sum. Let's take a look at this problem from the top down. At the end of this process, we know for sure that we're going to have to insert n elements into a final array size n. Let's take a moment to visualize these insertions as a line of length n. The next line we add is the size n over 2, and then we add a line of size n over 4, and then n over 8, and so on. Perhaps you're surprised. Even if we continue to do this until we reach 1 element, we never quite match the size of the original line. So, one cool approximation to the sum is that our total number of insertions can never be more than 2n. If you're more mathematically inclined, you can get a similar result by simplifying the sum using the geometric sum formula. And this means that in the scheme, the total number of insertions for n elements takes O of n time, which is significantly better than our other O of n squared scheme. So, having gone through this for how long it takes to do n
Yeah,
numbers,
2n minus
take a moment to
1.
think about the following question. What's the runtime for single insert operations in this scheme? This question actually ends up being intentionally ambiguous. There are really two ways to
2n,
answer it.
bro.
We just found a method to insert n elements in an array in O of n time. So one perspective to answer this question is that this means that on average, each insert operation is constant time, or in big O notation, O of 1 time. Computer scientists often like to call this the amortized runtime or average case runtime. Another way to think about this is in terms of the upper bound on how long a single insert operation takes. What's the worst case? Well, in the worst case, we end up inserting an element that requires a resize, which is going to require us to create an array that's twice the size of the current one and copy all the elements over. The runtime in this worst case is O of n. And both of these perspectives are completely valid. What you'll see in those data structures courses and books is that the running time of the insert operation in a dynamic array is O of 1 amortized and O of n in the worst case. So before I conclude, I do want to quickly mention a few other operations to take note of in a dynamic array. The insertion operations are only focused on the end of the array. If we wanted to insert an element in the middle of the array, we're going to have to shift all the elements over. This is to make sure that the indexing is consistent. Another important feature is removing elements, which really end up working exactly like insertion. You can remove elements from the end of the array in O of 1 amortized time and O of n worst case. The O of n comes from the fact that dynamic arrays don't want to waste too much space, so if after a series of remove operations, the array has less than half of its capacity, we resize the array by half of its size. And once again, if we remove an element in the middle of a dynamic array, it's going to take O of n time, and so we're going to once again have to shift elements to the left to keep indexing consistent. So to finish things off, what we have just done is we found a way to create a dynamic array that has a fast insert and remove operation. We can also add this element to super quickly come up with these schemes and design such a robust data structure. Really, at the end of the day, it was a try.
One fine afternoon, I get an email from Amazon for an application I filled 9 months ago. They had set me up a DSA interview in 4 days without any warning. I had not touched LeetCode in months, but at the same time, I knew I would regret if I didn't give my best now. So for the next 4 nights and 3 days, I solved almost 100 questions, and the only topic I didn't touch was advanced Java. I skipped to ZT
Brother.
because they are way more recurring. And guess what they asked me the first thing in the interview? Literally the hardest question from advanced Java. But I didn't know this at because I knew I would regret if I 9 months ago. They had set me up a DSA interview in 4 days without any warning. I had not touched LeetCode in months, but at the same time, from Amazon for an application I filled 9 months ago. They had set me up a DSA interview in 4 days without any warning. I had not touched LeetCode in months, but at the same time, I knew I would regret if I didn't give my best now. So for the next 4 nights and 3 days, I solved almost 100 questions, and the only topic I didn't touch was advanced Java.
100, bro. Look at the. He literally
Next 4 nights and
23 submission,
3 days, I
23 submission,
solved almost
21 submission. Oh my god.
100 questions, and the only topic I didn't touch was advanced Java. I instead chose DP because they are way more recurring. And guess what they asked me the first thing in the interview? Literally the hardest question from advanced Java. But I didn't know this at that time. I literally didn't even remember the names of algorithms like Dijkstra or Bellman code. And yet I somehow managed to solve the question with the most efficient time and memory complexity that someone could have come up with in an interview in just 35 minutes. Boom. Even I was astonished to find this out later after the interview ended. My prefrontal cortex had pulled up a divine clutch. Now, I didn't tell you this story just to show off. In fact, they still rejected me somehow. God, I hate Amazon. Can you guess how many In fact, they still rejected me somehow. God. I hate Amazon. Can you guess how many LeetCode problems I solved to reach this stage? 300, 500, 900, 150. Oh, sorry, less than 150. But I solved those same 150 problems 6 or 7 times. I don't even remember. So, my fellow worlds, what I'm trying to tell you is that 1. The number of problems you solve doesn't matter shit. 2. What matters is an in-depth understanding of the core problem-solving patterns, not just the algorithms, so you can come up with algorithms like Bellman code by yourself in an interview, like I did. Complete mastery of your programming language. Now that we have laid down the cornerstones, let's understand the actionable steps we need to take to get you there. The number 1 mistake people make is not spending enough time with a problem and jumping directly to a solution. I saw this Redditor the other day who solved 350 questions, but they would used to see the solution before even attempting the problem by themselves. It genuinely blows my mind that people do this. Look, before trees, I used to be really bad at coming up with solutions myself, but I made a rule to always spend at least 30 minutes with every single problem. At times, even over an hour. I'd come up with multiple approaches, try, fail, and repeat. If my brain couldn't come up with any solution,
Yeah, but the thing is, you cannot like come up with the
Mistakes of AI fundamentals in
Bellman Ford thing by yourself. You need a outside thing. Outside.
then I would at least try to code a brute force approach.
It's like if you've never seen it ever, or even once, it's gonna take forever. You're gonna be stuck in there forever. Minimum stack. Let's do it. See, like I don't want to do this kind of like bullshit. It's difficult. It's difficult. That kind of shit is difficult. Asteroid collision. Okay. You're given an array of tokens that represent valid arithmetic expression in reverse Polish notation. What the fuck does that mean? Check. Okay. So plus means. So 1 plus 2 multiplied by 3 minus 4 is equal to, okay, it skips one thing. Okay, let's implement a stack. It sounds like a stack question from the get-go. It's going to be an empty stack for I in tokens. If it's one of them, you gotta go if it's one of them, you gotta go before. You gotta do maybe I should do else if no, I mean if it's one of these, what do I gotta do? I think I have to stack of I minus 2 plus stack of I minus 1 output if it's not, none of this is true, I'm just gonna append, no, stack dot append. Like, okay, that's the logic. Let's just write the code. It's the same thing, right? When should I pop it? Should I pop? Yeah, I should pop. That's for addition. Let's give it a go. Um, I think I have to literally do this for like everything too. There's no programmatic way to do it. It's gonna look ugly. So I'm gonna, matter of fact, I'm gonna copy this and go. Matter of fact, I can just copy everything. Copy everything. Copy. Go down. Take out all of this shit. Go down here. Why does it look so ugly? Why is my code looking ugly as shit? Let's try this again. Oh, it's bro, this is the perfect code of all time. What the fuck? So stack minus 2 does not exist. Oh my god. Shit. I can do that. I can actually do that shit. Okay, let's try this. This is what I meant. This is what I actually meant. Why am I... Bro, this is actually what I meant. Clearly. I did it first time. Let's go. Let's try my method. Bro. It's gonna take forever. I didn't know you could do just pop. Yeah, it reduces a step, but I think this should work too. Oh, of course. Of course. It's gotta be N, comma I in new. It's gonna go look retarded, but it is what it is. I just want to make sure my code works and my idea works. I know it works, but what do I need to return? The output, return output. How is this out of range? I got the idea, but feels annoying. Feels annoying to do the walk of shame. I know this is gonna work because I came up with an idea myself. Why is there just one test case, bro? What the hell? So this should work. Just remember you could do that. What the hell? Brute force, no one cares. Doubly linkless, no one cares. Give me the stack though. Stack. That's what I meant, nigga. When you do it, it works. When I do it, it doesn't work. A, B, come on. Of course, A, B. Yeah. Both of them need to be popped out, of course. Bro, this is like some brutal mog. You're mogging me, son. Just mogging me. Mogging me. You're just mogging. Why you mogging like that, nigga? This nigga's just mogging. But anyways, that's just the point. Let's do another one. Start collision. Let's do another stack, nigga. Why is valid parentheses the only thing? Yeah, just give me that. I'll do the rest of them. But the code is just like this small. Yeah. Okay, whatever. So it has to be open, close, that kind of stuff. So for I in string, just don't give a fuck. Just don't give a fuck. It's using a hash map too. if this thing right there, if stack has, what if stack, if I, no, if I in close open, okay, -1 equals to close to C. I need to stack dot pop it if both of them are close or in there. I need to pop it, else return false, of course. Else, if it's not in there, just append the thing. Okay, that's kind of fun, but I didn't really finish that. I know I didn't really finish that, but it's kind of fun. Minimum search and rotate array. I need to do the rotate array stuff. Rotated array sounds fun. I need to do rotated array, and bro, if I do rotated arrays, this thing will be gone. That'll be fun. Nah. 2 pointers is always fun. 3 sum, not doing that. I'm still not good at hash, for fuck's sake. Bro, 26 easy. What even is that, nigga? 26 easy. Might as well not even do it. I need to do medium problems, but let's do a, I don't know, backtracking, just too much. It spikes my cortisol. Lowest common ancestor in search tree. Nah, I don't want to do randomly. I want to be focused, because this is like a DFS mainly is like a time sink, so I don't want
Even though
to
I
waste a
know
lot of
it's
time.
going to fail on time limit, but it's still a win because you learn a lot. The questions I hate the most are ones which get solved in 10 minutes because they don't even teach me anything. Having solved one extra question.
This is the goal, right? You need 80 medium questions done, and 70 hard ones. This is the, yeah, I mean hard ones, let's look at it. We don't even have that much hard. No, I mean, get this shit done. Yeah, we like about 7 hard questions that you need to like kind of memorize. You don't have to memorize it, but have like a deeper understanding, maybe. Let's see if this nigga has.
On my profile doesn't mean anything. So the key is to spend at least 20 or 30 minutes on each problem. The
Bro, this
second
is not even
mistake you will
true.
Often make
Interview with the top coder. No, competitive programmer.
Quick pause.
I think, yeah, okay. I just need to stick with the top triangle. Like, yeah. Anytime I come over. Again, it's the same thing over and over again anyway, so. Huffman quotes and information and theory perspective. Okay. Stack. Okay, I need a more introduction to building collision simulation and introduction to computer graphics. Graphics, it's in the name. Complete recursion visualization.
I mean, honestly,
No, I don't care. I just wanna fuck you up. Fuck you, Stack, BSA. They like to be alone. Of course, I understand it, but I need like a 1 hour visualize. Like, you don't get it. I want this type of video.
is not all on spot. This is literally impossible, you damn compiler, only to realize 45 minutes later that you misunderstood the problem in the first place. The second step is to come up with solution. I literally cannot help you here. This is completely up to your intelligence. The third step is to visually illustrate your algorithm. See if it passes all the test cases you wrote, compute its complexity, and I usually end up writing some pseudocode as well. The third mistake that people often make, and I used to for a long time, is copying the solution directly from the video. When you don't pass all the test cases and finally look at a video solution, you must resist directly copying the code solution. Instead, try to remember the code exactly and write it down by memory. Initially, it will feel like moving mountains, but gradually you will realize that this is very crucial in increasing the third point, complete mastery of a programming language. I would also highly recommend you don't use AI at all while solving DSA. For even small questions like how to insert an element in an array, you can very easily find solutions on Google. It is very easy to get addicted to ChatGPT, and before you know it, you are using it to solve complete problems. AI
Bro, this is like some retarded shit. It's like, don't use Google to write your essays. It's like the same thing over and over again. It doesn't matter. It's like a retarded ass thing.
Specifically, you develop enough concentration to persevere the 30 minutes.
Who the fuck is this nigga? Fucking pig ass. So okay,
Thank you.
this video. Focus on years of regular practice, not cramming in few days. He explicitly to get strong enough at contest. Mansford repeatedly solved program. Does he?
Nurse, and you have a chance to that if you are good there, Google might invite you to an interview.
Nice.
And after university, once you have a job already, maybe you start a family, you don't have time anymore to practice, like several hours a week, then why would you continue?
That's true.
Some people still do because they enjoy it, but not a lot.
I personally think it's a lot easier to just apply to these jobs normally than winning a competition. Do you think the coding questions for the interviews are similar to the competitive programming questions, or is it way easier?
So regarding the first question, how easy it is to get for competitions, it's not that you have to win, like Google Kickstart, to be invited top 200, maybe even top 500.
Bro, I'm not even like making fun of him. His head is literally like small. What the fuck?
That is enough.
You would think his head must be like really big, but it actually is kind of small.
That you can say that while applying, and maybe they will give you the first interview because of that. So you will put me fail if you aren't good, maybe in other areas. But it's a chance to.
You need to cranium max, bro. You need to take Loud HRT and Trenbolone. What the fuck?
Compared to thousands of people, maybe tens of thousands. And problems are similar. Competitive programming is harder because it's for people that train sometimes years for that. It needs to be harder. But there are just some differences. While competitive programming requires some complicated algorithms, coding interviews sometimes can ask you questions that aren't possible to be tested with computer, like maybe some parallel computing with thousands of machines. You will not need such a problem in competitive programming because organizers don't want to get thousands of machines to test your program. Google organized such a competition, one with hundreds of machines testing your program, but it had some limitations. It was called distributed coaching.
Cool.
Coding interviews have also sometimes other problems that cannot appear in competitive programming, like, for example, inventing an algorithm that will work in constant time for something, or in logarithmic time. Given an array binary search some number, because the array is sorted, it's very hard to test with competitive programming because you need to get that array anyway. So the time spent by computer or checker for that needs to be competing with them in team ICPC competition. Here I am.
That's pretty cool. That's pretty cool. What about Gennady? Like, when did he start? Like, how old is he now?
I think he started when he was like 6 with coding, and when he was 11, the first time he was in International Olympiad for high school.
Okay.
And I think for the first time when he was there, he didn't win. He won when he was there.
Okay. Yeah. Wait, how old is he now?
My age or maybe 1 year older. I think he's 25. Don't quote me on that.
Okay, that's cool. So what do you plan to do in the future? Like, do you think you just want to teach competitive programming, or do you want to do something else? You know, what if everything paid the same? Every job paid the same. What would you choose?
Can I just play games on PS4?
You have to stream it.
Okay.
Oh, so I guess you like playing games on PS4s?
Yes, but algorithms are also cool. If I were to choose just till the end of my life to do algorithms or play games, I would choose algorithms because those are more interesting to me.
Cool.
It's cool to do some of this and some of that. If everybody paid if everything paid the same, then I for sure would continue with my YouTube channel, where for now I don't even have ads, so I earn zero for now for that, and I don't think it will change a lot in the near future. But I know that I help some.
It's a lot of Fibonacci series and shit like that.
They think they understand how to do it, but if a bunch of time goes by, they're probably not going to be able to do it again. Kids learn the same way adults do, with repetition, right? So that's a pretty simple answer, repetition. So why don't more people do it? I mean, it just sounds so simple. Why don't more people do repetition when it comes to LeetCode? Let me kind of explain the classic problem people make when they solve LeetCode problems. Let's say they're solving a medium binary search problem. And I bet you most people who try to solve a like medium level binary search problem, they're probably not even super good at like basic binary search. But okay, they try to do it. It takes them probably some cognitive energy to even implement basic binary search. You know, if it takes you 10 minutes to implement basic binary search, that's a problem. You shouldn't even be attempting medium problems. If it takes you, 10 minutes to figure out that this number is 234, why are you doing addition? You don't even know what this number represents, right? You gotta get really, really good at the basics before you kind of take steps beyond that. But okay, just continue. You get to a medium binary search question, you realize that it's a binary search question, but you still can't solve it. All you have is your basic binary search algorithm implemented. Then you look at the solution, it takes you maybe 1 hour to understand the solution. But you're able to do it. You write your code, you kind of really exercise your brain muscles, you write it, and now you're done for the day. Then you continue solving the code problems. Maybe a month later, you solve another medium binary search question. You're not able to solve it. You look at the solution, it takes you some time to figure out the solution. Once you realize it's binary search, you feel bad. You realize it's similar to a problem you've already solved, but you weren't able to figure it out again. Why not? Because you tricked yourself. You think you understand the solution, and maybe you did for a very short time, but that didn't really sink in. And it's not your fault when you're learning something that's genuinely difficult. Like if you're reading the solution to a problem, it's difficult, and you think you understood it, which you might have, but it didn't sink in. So of course you need repetition. It's such a simple answer, isn't it? Just practice. But then why isn't anybody doing it? This is how you learn pretty much everything in life. When you learn how to read, it takes practice. Why don't people do it when it comes to LeetCode? I don't know, but let's be honest, I made the same mistake until I realized this. I thought like, I did so well in high school, I did so well in math and physics, so why am I so bad at LeetCode? Because the way I'm practicing it isn't enough. LeetCode is difficult. It's difficult like math and physics, but it's not more difficult. You could not teach somebody how to count and add numbers and divide numbers in a relatively short time without practicing. So now let me try to give more concrete advice on how to practice, how to actually do repetition, because even that isn't as straightforward as you might expect. First of all, there are certain core algorithms. Algorithms like binary search, DFS, depth first search, breadth first search, sliding window, and a bunch of other kind of core algorithms that I talk a lot about on this channel, as well as like you can check a lot of this stuff out on LeetCode.io. But
Okay, let's do a binary medium. Rotated, this one. So I need to rotate it, and this is a binary search. So the way he did it, it was kind of confusing. Backtracking is cool. Trees, I don't really understand trees.
During World War II, the military noticed that the wings and tails of the returning aircrafts got cold, so they decided to add more armor to those parts of the plane, but one nerd strongly opposed to the idea. He said that by only examining the plane that didn't blow up and completely neglecting the planes that blew up, we missed the most fragile parts of the plane where one direct hit would instantly crash the plane. Sounds familiar? This phenomena came to be known as survivorship bias. It's a common logical fallacy that occurs when we only examine the successful group and completely ignore the failure. We only tend to see the most successful people and their interviews, because no dog who cracked a 5 LPA job is going to brag about it. Outside Fang and similar companies, no one takes GSA focused interviews. Almost every other country, yes, even those remote European firms, do focus on your actual skill set and experience. And in college placements, yes, companies might ask you GSA questions, but only the bare basics. Again, the focus is on your core fundamentals like OOPC and OS and your gender, along with whatever you have mentioned in your resume. Now, some YouTubers are going to kill me for saying this, because their entire business is built upon lies and deception. I myself fell hard for their trap and ended up wasting several months on DSA. And outside of Amazon, the only DSA questions I got asked were these. Now I'm going to be completely transparent and not hide the fact that sometimes you might encounter these or even craft problems in OAs. But I'm also not going to pretend that everyone just solves them on their own. I'm not encouraging you to cheat, but you're gonna do it anyways, don't you? Like, if everyone else is cheating, then is cheating even unethical, or is it just an adaptive strategy? But hey, I'm also a single data point, so you don't need to take my word for granted. Instead, ask the internet. Ask people who have gone through several interviews and not just the top earning engineers. Inquire your seniors, placement cell, and take everything into account to form a decisive conclusion for yourself. Also, there's a
Okay, let's do some. Get back to some.
my personal advice to you would be get really, really good at these basics. Practice them a lot. You can do that at the same time that you're solving LeetCode problems, or you can do it before you start solving LeetCode problems. But you want to get good at it, and I promise you, it won't take you that long. The target that most people set when they're solving LeetCode problems is, I want to be able to look at a LeetCode problem and solve it quickly. That, in my opinion, is the wrong target. You should get really good at just 4 algorithms. That should be your target. At least that should be your first target. And binary search, it's a very short algorithm. What is it, like less?
Okay, this is all like fine. I need to do BFS. Let's actually like look at things a little bit more objectively. Let's forget all of this shit. Let's go back to, do I want to read the paper? I don't really like feel like it. I wanna matrix, that's like one way to like do it. Okay. I need to look probability. I need to learn some probability stuff, and I'm gonna do it right now. Where is AI? AI. Okay, I need to make a call. சரி நிறைய மீட் வாங்கிதாங்க நிறைய மீட் வாங்கிதாங்க மீட்
imaginary black person wants to use the word like that, obviously that's their right. It was not censored though. I had to go into CapCut and censor that. Here's what I want to tell my fellow whites about that video. Putting aside the disturbing amount of white people in the comment section being like, see, she's saying the quiet part out loud, they want us dead. I've seen a lot of white people getting butthurt about that clip. I've also seen some people getting butthurt because of some of the panels that were on TikTok Live the other day.
Okay, let's just. Nigga, where is my AI tutor? Probability for ML/AI. I think if you can get an intuitive sense for George Morgan contribution, foundation, axioms, and probability and their interpretation. So, bro, why is this goaded? Why is stochastic process and Markov chains? What the bro? Look at this, bro. Holy shit. Whoa. Okay, I just need the outline. I don't. Amen. Let's look at this nigga. Who the fuck you with, nigga? Bernoulli. What the fuck that is? Bernoulli. Who is he? What kind of man are you? What the fuck?
If you've ever taken a science or math class, you're probably used to lots of things being named after the same people. There are hundreds of principles and theorems and equations named after superstars like Euler and Laplace and Gauss, so it might not seem all that...
Bro, Gauss, that nigga's goated. Fuck. Get the F. Keep my wives. What am I thinking? This guy, Bernoulli. Fuck. What was I thinking? Bro, look at that.
Weird to learn about Bernoulli's brachistochrone solution, Bernoulli's equation in fluid dynamics, and the Bernoulli...
Secretly, alchemical medicine is age, Newtonian mechanics. Daniel Bernoulli, the famous principle of fluid dynamics, secret correspondent with, was a mystic and seer and a spiritualist who claimed to visit heaven and earth. Okay. Jacob Bernoulli, the theory Bernoulli distribution. Okay. Hidden works in numerology and divine probability. Ooh, give up. Okay. Jacob. They should have like a tree branch kind of system. It's easy to go back. His own work, art of conjecture, even the finite enclosure with infinite series and an unlimited limited appears, so soul mostly dwells in a minutia and the narrows limits finite itself. This is a hermeneutical numerological verse showing the occult influence. Okay. Contains Pythagoras number mysticism, defines the divine proper family correspondence.
Probability distribution, and you would assume that they're all named after the same person, but they're not. In the 17th and 18th century, there were actually 8 mathematically gifted Bernoullis from 3 generations of the same family. But 3 of the Bernoullis really stood out: Jacob, Johann, and Daniel.
So who is this nigga?
They were all descendants of Nicholas Bernoulli, who was born in 1623. Nicholas had 3 sons who were named Jacob, Nicholas after himself, and Johann. The younger Nicholas became a painter and a city official, but his brothers were famous mathematicians. Jacob, the oldest, solved a number of early calculus problems that are still taught in schools today. But Jacob's most important discoveries were in probability. He was the first.
Bro, he looks like he's wearing like a chainmail helmet. Like, you know what I mean? One of them Assassin's Creed's chainmail helmet. What the fuck is this Washington ass cut, man? George Washington ass cut. What even is that expression? Like, what are you trying to like say? Okay. So let's go back. Probability key distribution, Bernoulli distribution, and binomial. This is the binomial distribution. So binomial meaning the normal distribution. The fuck is a Bernoulli distribution, nigga?
Hello again. In this lecture, we are going to discuss the Bernoulli distribution. Before we begin, we used Bern to define a Bernoulli distribution, followed by the probability of our preferred outcome in parentheses. Therefore, we read the following statement as variable x.
Okay, probability is equivalent. What the fuck is this symbol?
Follows a Bernoulli distribution with a
okay. Probability.
the probability of 6.
So Bernoulli distribution Bayesian is proportional to. Okay. The probability is proportional to the Bernoulli distribution.
Okay, we need to describe what types of events follow a Bernoulli distribution. Any event where we only have one trial and 2 possible outcomes follows such a distribution.
One trial, 2 possible outcomes. So let's take a psychology bitch and tell her there's 2 probable. Okay, whatever.
A single true or false quiz question, or deciding whether to vote for.
Okay, one trial, 2 outcomes, meaning not a leftist right? Oh shit,
Take a look at the Bernoulli
no.
distribution, another important discrete probability distribution. As an example, suppose we toss a fair coin once. What is the distribution of number of heads in that single toss? Well, it's going to have a Bernoulli distribution. Suppose we have a single trial, where each trial can result in one of 2 possible mutually exclusive outcomes. I'm going to label those below.
It's a binary decision. It's a single binary decision. It's called a Bernoulli distribution. Failure is going to be -1. Okay.
Probability of failure must be 1 minus b. We're going to let the random variable x equal 1 if the success occurs, and 0 if a failure.
So success is equal to failure is equal to 0. So P of 0, P of failure is going to be. So this is the formula. Okay. P of 1, probability of 1 of it being successful would be basically 0. Sure, P of 1 again. Interesting. So it'll be 1. Okay. Oh.
Failure occurs. These conditions hold that x has what we call the Bernoulli distribution, where the probability the random variable x takes on the value little x is equal to p to the x, 1 minus b to the 1 minus x. And we sometimes write this as just little p on x. You might see it written that way sometimes. Now what we should do is say what values x can take on, and so we write here for little x being equal to 0 or 1. And so all of this we refer to sometimes as the probability mass function of the Bernoulli distribution. And if we were to write this out for the individual values, we see the probability the random variable x takes on the value 1 is equal to p to the 1, 1 minus p to the 1 minus 1, which is just equal to p. And the probability that the random variable x takes on the value 0 is equal to p to the 0, 1 minus p to the 1 minus 0, which is just 1 minus p. The probability of success and the probability of failure that we talked about previously.
What we have up here is just a way of writing that in one line.
So this is the idea. P of 0 will be this one, P of 1 is equal to 1, okay. P of 1 is equal to 1 minus y. Ooh, I'm gonna give BJJ a specific application. So, yeah. Bro, I actually love this. What the fuck? It's like, I don't know. Machine learning application. Fine.
Now it can be shown without too much difficulty that the mean of a Bernoulli random variable is equal to p, and the variance of a Bernoulli random variable is equal to p times.
Mean. How is the mean that
1 minus
thing?
p.
Okay.
Approximately 1 in 200 American adults are lawyers. Suppose we randomly sample one American adult. We might ask ourselves, what is the distribution of the number of lawyers? If we run a single trial, each person is a lawyer or they are not, and the conditions of the Bernoulli distribution here are satisfied. So the number of lawyers is going to have a Bernoulli distribution with parameter p. And p is going to be simply the probability that any one individual person is a lawyer, which is called 1 in 200. And if we let the random variable x represent the number of lawyers in our sample size 1, then the probability that the random variable x takes on the value real x is going to be equal to p to the x, which is 1 over 200 to the x, times 1 minus p, which is 1 minus 1 over 200 to the 1 minus x. And this is for x equaling 0 or 1, because we either going to get one lawyer or none. And if we substituted these values in here, we'd see that the probability that we do get one lawyer is going to be equal to 1 over 200, and the probability that we don't get a lawyer, we get 0 lawyers, is going to simply be 199 over 200. Now you might be wondering, what is the point of all of this? We have that approximately 1 in 200 American adults are lawyers, so it's certainly not rocket science to say the probability that we get one lawyer is 1 in 200. But saying that something has a Bernoulli distribution is a nice, concise description of the situation at hand. Some other common discrete probability distributions are built as concise description of the situation at hand. Some other common discrete probability distributions are built on the assumption of independent Bernoulli trials. For example, here we have the binomial distribution, the geometric distribution, and the negative.
So just like an inverse of a probability. I mean, negative of a probability. Okay.
The binomial distribution is the distribution of the number of successes in n independent Bernoulli trials. The geometric distribution is the distribution of the number of trials to get the first success in independent Bernoulli trials. And the negative binomial distribution is the distribution of the number of trials to get the rth success in independent Bernoulli trials. And so we have a number of these other distributions that are built on this assumption of independent Bernoulli trials. And we'll talk about some of those distributions a little bit later on. Let's look at an introduction to binomial distribution. Suppose there are n independent trials.
Binomial. Binomial is... binomial. Don't really fuck with binomial like that. I wanna... It's like a binomial would be the midwit graph thing. This is like the physics thing. Okay, let's take a look.
Thanks to Curiosity Street for sponsoring this video. Watch thousands
What's the worst that can happen?
of documentaries and get access to Nebula for free when you sign up using the link in the description. Bernoulli's equation is a simple but incredibly important equation in physics and engineering that can help us understand a lot about the flow of fluids in the world around us. It essentially describes the relationship between the pressure, velocity, and elevation of a flowing fluid. It has countless applications. We can use it to explain how planes generate lift, or to calculate how fast liquid will drain from a container, for example. We'll explore these applications and a few more later on, but let's start by reviewing the equation itself. It was first published by the Swiss physicist Daniel Bernoulli in 1738, and it looks like...
Daniel Bernoulli. Daniel Bernoulli, isn't that the bad baby? Yeah, I don't really fuck with his name, bro.
Like this. The equation states that the sum of these three terms remains constant along a streamline. Each of the terms is a pressure. The first term is the static pressure, which is just the pressure P of the fluid. Then we have the dynamic pressure, which is a function of the fluid density, rho, and velocity, v. It represents the fluid kinetic energy per unit volume. And the last term is the hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is gravitational acceleration, and H is the elevation of the fluid, which is just its height above the reference level. This is the pressure form of the equation, but it can also be presented in the head form and the energy form. We can think of Bernoulli's equation.
What the fuck? This is a pressure form. What's going on here? Okay.
As a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy
Pressure, energy. Bro, what are these energies? Just making it up.
remains constant. This is really valuable information that can help us
Uh-huh.
analyze a whole range of fluid flow problems. The equation does have a few limitations, which I'll cover later on in the video. But for now, the important thing to note is that it can only be applied along a streamline. We can define a streamline in steady flow as the path traced by a single particle within the fluid. Or more technically, as a curve that at all points is tangent to the particle's velocity vector. Let's look at an example where we apply Bernoulli's equation to flow through a pipe which has a change in diameter. We want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations, so we can rewrite it like this, with points 1 and 2 both being on the same streamline. There's no significant change in elevation between points 1 and 2, so the potential energy terms cancel each other out. And if we put all the static pressure terms on one side, we get this equation for the change in pressure. If we assume that the fluid is incompressible,
Bro, I've seen this equation. What the fuck?
the mass flow rate at points 1 and 2 must be equal. This gives us what's called the continuity equation, which is just a statement of the conservation of mass. Mass flow rate. By this concept that for horizontal flow, an increase in fluid velocity must be accompanied by a decrease in pressure. Shear force.
Well, actually, the Earth is flat. Bro, this is like the most popular? No way. People believe the Earth is flat. No way. But the issue is none of these guys know any math, so it doesn't really matter.
Calculus is a fundamental tool in engineering. It helps us stabilize drones in flight. Predict how structures deform under loading, and model the dynamics of vibrating systems. In all of these cases, we're asking the same fundamental question. How does the system respond when something changes? Calculus is how we answer that question. It's the mathematical study of change. In this video, we'll explore the key principles of calculus and discover exactly how they apply to real-world engineering problems. The easiest way to understand how one quantity is affected by changes to another is by plotting both on a graph. The slope of the graph, represented by a tangent line that just touches the curve, is a key piece of information. It tells us how sensitive one quantity is to another, and that sensitivity changes depending on where we are on the curve. The slope often has a real physical meaning. If the graph shows displacement on the horizontal axis and force on the vertical axis, the slope represents the stiffness of the object, like the stiffness of a spring, for example. If the graph shows velocity versus time, the slope is acceleration, and if it shows voltage versus current, the slope is electrical resistance. To understand how to extract this slope information in a systematic way, let's look at a simple example, the function y equals x cubed. Say we want to calculate the slope of this curve at a particular point. One way to approximate it is to pick another point slightly to the right, at x plus a small amount that we'll call delta x. The straight line between these 2 points gives us an estimate of the gradient of the curve at this position. Gives us a slope equal to the change in y divided by the change in x. Now imagine moving the 2 points closer together, shrinking delta x towards 0. As the points get closer, the line connecting them becomes a better and better approximation of the tangent at the point. And as delta x tends towards 0, the line between the 2 points becomes the true tangent, giving us the exact slope at that point. By expanding the slope equation and taking the limit as delta x tends towards 0, we obtain an equation that gives us the slope of our x cubed function at any point x, dy over dt. Engineers a partial derivative, which means we're looking at x. And so the rectangle approximates a tiny contribution to the total. 1,300 joules per second consumed over 0.1 seconds is 100.
What if I told you that creativity, something we usually think of as wild, mysterious, and unexplainable, actually follows mathematically sudden, chaotic, impossible to predict? But researchers like Dean Keith Simonton, a leading psychologist of creativity, argue otherwise. He studied thousands of works by composers, scientists, and inventors, and found something surprising. Creative success follows statistical probability. The more attempts someone makes, the more likely they are to produce a masterpiece. In other words, creativity has a law of large numbers. Think of Thomas Edison. He filed over 1,000 patents, most of them forgettable. But hidden in that pile were the light bulb and the phonograph. Same with Picasso. He created more than 20,000 works, but only a fraction define him today. Mathematically, it's simple. Quantity breeds quality. Every attempt increases the odds of a breakthrough. Chapter 2. Zipf's law and idea distribution. But it's not just about trying more. There's also a distribution pattern in play. Enter Zipf's law, a principle from linguistics and mathematics. It says that in any large set, the frequency of outcomes follows a predictable curve. A few things are extremely common. Most are mediocre. And a tiny fraction are extraordinary. Apply this to creativity. Most of your ideas will be average. Some will be pretty good, and a rare few will be brilliant. That curve shows up everywhere. Hit songs, best-selling books, viral TikToks. Mathematically, most creativity is noise, but the signal is in the outliers. Chapter 3. Combinatorial creativity. Another formula for creativity comes from Margaret Bowden, a pioneer in cognitive science. She argues that creativity is mostly combinatorial, taking existing elements and recombining them in novel ways. If you model this mathematically, it's like permutations and combinations. Scientific theories. Chapter 4, the 10,000 hour and exponential growth curve. Then there's the role of time and effort. You've probably heard, but as hours accumulate, ability accelerates, and breakthroughs become more likely. Think of it like compound interest, underneath summating angle. But in between.
Okay, doesn't really matter. This is all science slop. This is all slop. This is all slop. Bernoulli distribution. It's basically distribution and classification. Poisson distribution.
Hello again. In this lecture, we are going to discuss the Poisson distribution and its main characteristics. For starters, we denote a Poisson distribution with the letters P and a single value parameter, lambda.
Oh, this shit is putting me off.
We read the statement below as variable y follows a Poisson distribution with lambda equal to 4. Okay. The Poisson distribution deals with the frequency with which an event occurs within a specific interval. Instead of the probability of an event, the Poisson distribution requires knowing how often it occurs for a specific period of time or distance. For example, a firefly might light up 3 times in 10 seconds on average. We should use a Poisson distribution if we want to determine the likelihood of it lighting up 8 times in 20 seconds. The graph of the Poisson distribution plots the number of instances the event occurs in a standard interval of time, and the probability for each one. Thus, our graph would always start from 0, since no event can happen a negative amount of times. However, there is no cap to the amount of times it could occur over the time interval. Okay, let us explore an example. Imagine you created an online course on probability. Usually your students ask you around 4 questions per day, but yesterday they asked 7. Surprised by the sudden spike in interest from your students, you wonder how likely it was that they would ask exactly 7 questions. In this example, the average number of questions you anticipate is 4, so lambda equals 4. The time interval is 1 entire workday, and the singular instance you are interested in is 7. Therefore, y is 7. To answer this question, we need to explore the probability function for this type of distribution. Alright, as you already saw, the Poisson distribution is wildly different from any other we have gone over so far. It comes without much surprise that its probability function is far different from anything we have examined so far. The formula looks as follows. P of y equals lambda to the power of y times the Euler's number to the power of negative lambda over y factorial. Before we plug in the values for our course creation example, we need to make sure that you understand the entire formula. Let's refresh your knowledge of the various parts of the formula. First, the E you see on your screen is known as Euler's number, or Napier's constant, as the second name suggests. It's a fixed value, approximately equal to 2.72.
Yeah.
Observed in physics, mathematics, and nature. But for the purpose of this example, you only need to know its value. Secondly, a number to the power of negative n is the same as dividing 1 by that number to the power of n. In this case, e to the power of negative lambda is just 1 over e to the power of lambda. Right. Going back to our example, the probability of receiving 7 questions is equal to 4 raised to the 7th degree multiplied by e raised to the negative 4 over 7 factorial. That approximately equals 16,384 times 0.0183 over 5,040, or 0.06. Therefore, there was only a 6% chance of receiving exactly 7 questions. So far, so good. Knowing the probability function, we can calculate the expected value. By definition, the expected value of y equals the sum of all the products of a distinct value in the sample space and its probability. By plugging in, we get this complicated expression. Eventually, we find that the expected value is simply lambda. Similarly, by applying the formulas we already know, the variance also ends up being equal to lambda. Both the mean and the variance being equal to lambda serve as yet another example of the elegant statistics these distributions possess and why we can take advantage of them. Great job, everyone. Now, if we wish to compute the probability of an interval of a Poisson distribution, we will take the same steps we usually do for discrete distributions.
So let's take an example for the amount of time UFC was in London every year. So in average it's like 3 times a year. I mean 2 times a year. Okay. Okay, just randomly happening or independently. Okay, it's not. It doesn't have any algorithmic, medical, logical basis. Cool. So random variable. So on a random event is 3. So when so let's say 2, the average is 2. Okay, the average is 2. The 2 is over here. So it happens 7 times this year. So 7, 7, 2 goes here, 7. Okay, cool. Yeah, random, pretty random. It's a count. It's a period though. It's like average weight. Yeah, doesn't matter. Yeah. No. It's like a shotgun, someone like shooting a shotgun. No. This is Prasan. Hmm. Yeah. But yeah, it's tiny probability and not only that. It also the big spikes don't happen. That's why. Yeah, the number of fatalities might change because sometimes like a small plane might crash, sometimes like a big passenger plane might crash. So the second one, not really.
this video, we're going to focus on solving probability exponential distribution problems. So let's start with this problem. Laptops produced by company XYZ last on average for 5 years. The lifespan of each laptop follows an exponential distribution. Part A, calculate the rate parameter. The rate parameter is represented by the symbol lambda. Now, in order to calculate the rate parameter, we need to know what real is. In this case, the average. The average is 5 years. Now, the rate parameter is 1 over lambda. So that's going to be 1 over 5. 1 divided by 5 is per total. And the units is going to be years to the minus 1. So that's how we can calculate the rate parameter. It's very straightforward. Now, part B, provide the probability density function, and then we'll graph it. The probability density function is represented by f of x, and f of x is equal to the rate parameter lambda times e raised to the negative lambda.
Joint probability for multiple variable. I think it's like it's in the conspiracy theory shit where people have number of conspiracy theories. Let's say, the Jewish conspiracy, the Freemason conspiracy, and whatever, I don't know, like a third conspiracy. They see, okay, there's something going on here, and they try to add all of the conspiracy and be like, oh, something's happening, but that's not how it works. It's like, oh, there's 1 in 200 chance something's about to happen, and they like try to like find 200 other examples and try to like make it like a 1 in 1 probability, when it doesn't work like that. I think that's what it means. I might be wrong. Basics of joint probability. Independence and dependence.
Various kinds of machine learning statistical algorithms, it's important to understand how to manipulate the probability distribution. Talking about probability distribution of multiple variables, one of our most basic concepts is the idea of marginalization. When we compute the marginal distribution of some subset of variables in a joint probability distribution, we're computing the distribution that we would get if we restricted our attention only to that subset of the variables. That is, imagine that you had samples from both x and y together, but somebody came and threw away all the y's. The resulting distribution would be the marginal distribution over x. As our starting point then, if we had a joint distribution over just two variables, x and y, then the two marginals available to us are p of x and p of y. For discrete distributions, we compute marginals by summing over the variables that we're not interested in. This is sometimes called the sum rule of probability. For continuous random variables, we compute marginals by integrating out the variables that we care about. Here we can visualize marginalization in a discrete distribution in which y has 3 possible outcomes and x has 5 possible outcomes. The probability mass function is then a table with 15 entries in it that all sum to 1. To compute the marginal distribution over y, we would sum over the rows. To compute the marginal distribution over x, we would sum over the columns. In the continuous setting, it's a little bit hard to visualize things, but conceptually it's the same. This orange surface represents a joint probability density function over x and y. If we were to separately integrate this PDF over its two axes, we would get two probability density functions representing the marginals p of x and p of y. Having established the concept of a marginal distribution, we can now define conditional distributions. Conditional distributions fix a subset of variables and then ask what the resulting density is on the remaining variables. For both discrete and continuous variables, we get the conditional distribution by dividing the joint distribution by the relevant marginal. The only difference is whether we sum or integrate in order to compute that marginal. When we talk about conditional distributions, we say something like probability of x given y, and we use a vertical bar to denote that. Let's imagine going back to our discrete PMF from earlier. We compute the marginal distribution for the three outcomes, y1, y2, and y3. Now, if I wanted to talk about the distribution over x given that y equals y2, I would essentially ignore the other two rows.
Bro, some of these guys have like a sadistic way to like make it sound complicated than it really is. I wonder how many people really kind of do that. You know, they just want to like make it sound like, look at this, bro. Like, come on, this is not that deep. It's not that deep. Like, I don't want to click this. Make it something easy, please. Model the Titanic passenger model. Marginal probability, joint probability. Okay, add on it now. Joint probability. Conditional probability. Yeah, conditional. We kind of know it. It's pretty much similar to the conditional variable. Similar. Yeah, they have like a weird like thing, don't they? Just realized. What the fuck
shear
is this
force,
now?
and bending.
Joint density function. Nigga, what? Continuous random variable introduction.
Ways we use a probability that if small will be okay because the probability density.
It's like you gotta put your face, you gotta like actually do that. It's yeah, this is kind of like if you put your face at least. I think it's much more like a better way to like explain using your hand gestures and whatnot. Joint pro. Look at this kid. This kid is teaching you. Oh my god.
This is Jacob Barnett. At 2 years old, Jacob was diagnosed with autism. It was predicted he would never speak or know how to tie his shoes. But instead, Jacob was a child prodigy, graduating a physics teacher at the age of 13. Now, Jacob doesn't think of numbers like most of us. When he thinks of a number, he sees a mosaic of remarkably beautiful shapes. But instead of telling you how it all works, I'm going to show you, starting with the number 1. Have you figured out the pattern yet? If you click the link in the description, you'll see a program I created that generates these diagrams automatically. Try typing in any number and see what it looks like.
Bro, this is some severe like retardation. You don't want this. I know he's like better than me and whatnot, but whatever. Whatever, I will beat the fuck out of you, so it doesn't really matter. Probability distribution. No, I want to learn what joint PDF is. I mean joint distribution.
Here are the top 10 most important things to know about probability. Must know number 1, experimental probability. Let's start off by doing an example where we conduct
Okay. Marginal probability. Basic probability. Okay, let's do this. Marginal and conditional. Conditional, you can kind of visualize what it means, but what is marginal? An introduction to continuous marginal distribution. What the fuck does that even mean, bro? Like, give me like a proper. Is it Tamil? Does lead code have probability? Lead Cody. Problems. Go on problems. Want to see Euclidean. Where is memoization? It's combinatorics. Number theory. Number theory is. Did they even ask number theory? Probably not. Bit manipulation. Matrix. I wanna get good at that matrix shit. Greedy. Shell, suffix array, probability and statistics. It's all medium and hard. I will get good at it one day. No, don't explore, nigger. Fuck. All of them are wrong though, so it doesn't matter if it's like I made a submission, but if it's wrong it doesn't matter. So let's go. Probability. Nah, it's not a good video. Conditional probability and their uses. Okay, marginal and conditional, it's pretty similar. So what is it? Who created all of this shit? Joint PDF. Nigga, what the fuck is joint PDF? Was not an occultist. His work is actually kept in European through occult explanation towards mathematics and who worked in celestial mechanics and probability like Newton physics to show the solar system could be explained without invoking a divine or occult invention. Fuck you. Is famous. I had no need for hypothesis, referring to North's God intervention in his equation, brother. Bomba clad. I'll prove you wrong. Don't worry. Lapaz demon is thought an experiment as a hypothetical intention, or demon is just a metaphor. Okay. Many sources of describing Lapaz moving away from church, likely being an atheist or not. Okay. His works is often cited as a philosophy of theology, debates his historical associated with secular mathematics, science. Okay, then occult tradition. Fucking idiot. Fucking idiot. Okay, let's go. What the fuck is the probability? Density function. Mar-a-Lago, nigga. Pa. Okay, normal distribution. Okay. Bro, why am I in there like that? Probability density function would be the normal distribution, and the cumulative density function would be the sigmoid function over there. Okay, CDF is like the template. It's not really like a template. It's when like your teacher like holds your hand and like trying to like teach you how to like write in cursive. It's similar to that. Okay, PPF, CPF. CPF is like the giant child font function. Okay, I mean looks like doesn't look like a child, so I don't know. So this is like your teacher holding your hand to like write, and this is your uncle holding your hand to teach you how to jerk off. That's why it's erect. I'm such a genius. Is this the guy Tom will need? No way. I want to do let's see. I want to do a study. But I have a hypothesis on certain things. But let's see if I can do it or not. Okay, let's what is this binary clearly? Okay, let's look at this nigga and let's look at him. And marginal probability and its derivation, conditional, marginal, independence, Bayesian interference for ML. Monte Carlo simulation. Heard Monte Carlo simulation before. Is it something to do with bro, sweet. It's okay. Mm-hmm. Bro, good work of explaining nothing. I'll give you a follow though. Okay, how long have I been? Okay, I'm